Are we just using the chat box?
I think at that point we can go back to turning the mic on and asking questions live or chat, whichever is more, depending on what you have access to. Like if you're joining on a telephone where you don't have a microphone, then the chat window might be more effective. So yeah, we'll try to make it work the same as if we were all sitting together somehow. But if you have dogs barking in the background or children screaming in the background, no, I'm just saying it happens, then the chat window might be helpful for that reason instead, right? And yes, and mute. And no one has to be on video if they don't want to be, but you're welcome to be. It depends on the bandwidth that you have available to you, how this is best going to work. So. And if you just rolled out of bed, also true. Yeah, it's like I'm at home. Does that mean that I get to wear my old crappy home clothes, or do I like still pretend like I'm in professor mode and do my hair? Yeah, it's an interesting thing. It's like, okay, do I do professor mode with the sweatpants? Is that how this is going to work? I'm not sure. Stay tuned to find out. But yeah, now we got the screen share, we got the microphone, we got the streaming. Had questions from before class, just in case any of you are in the same position here. This program that I use, this is called OBS. I believe it stands for Open Broadcast Software, something to that effect. It is free. It is able to record lectures, so you can record them to a local device. But what I'm doing rather than recording them locally is having them stream directly to my YouTube channel, which is also free. So it takes a minute to get the conversion set up to get everything playing nicely together, but after that, it's super easy. So if anyone has questions about how to make this kind of thing work for the classes that you're teaching or any other types of things that you're going to have to be doing where you might have to do the same sort of thing, I'm happy to help you troubleshoot that. So it couldn't be easier, honestly, once you get it working. I really hope that Canvas and Icon and all of those things don't become overloaded, but if they do, then there's always the YouTube to get you through. So anywho, slide 20, categorical predictors. So up to this point, we fit general linear models. So those are models designed to predict quantitative outcomes. And we've examined one type of model that has one quantitative predictor. So we looked at, for instance, family income is predicted by years of education, where the quantitative predictor, we first had to center it so that 0 makes sense. So in your homework 3, I have some troubleshooting tips at the top in the instructions, but I wanted to point them out to you. When you're going through your homework and you're putting in your models, if you get the residual variance correct for a model, then you have the right model. You have the right outcome variable and the right predictor or predictors. If you get the intercept correct, then your predictors are also centered accurately per my instructions. If the intercept is wrong, then that likely points to a centering problem. So you'll have to make sure that the predictor that you're putting in your model is the centered version. For instance, if I have pleases centered at 5, is that right, I think? 7, yeah, fits centered at 5, something along those lines. So make sure that's the version of the predictor that's going in. For categorical predictors, the same thing applies, where we have, in this one case, a binary variable. So somebody's got to be the 0 and somebody's got to be the 1. In general, we'll see this more next time. If we have a categorical predictor with big C categories, that means we need big C fixed effects to be able to distinguish all the different categories. In practice, that translates to an intercept, which is going to be the expected outcome for the reference category, category 0, and then we'll need C-1 predictors, and they'll each have a slope that then distinguishes those. So in the simplest case with just a binary predictor, we only need to put one predictor in the model, and that is whether or not the case in each row is a 0 value or a 1 value. So if we're doing it this way, so now X here in the slide 21, X is a binary predictor. Somebody's the 0 and somebody is the 1. It's up to you who's the 0 and who's the 1. It doesn't actually matter. It's just deciding who your intercept is going to represent as the UR here sign. By the way, for those of you who've had stats classes before, What I'm talking about when you have a binary predictor of a quantitative outcome, that is what's known as an independent or two samples t-test. We use t for lots of things, so that's not the best name, but that's what I'm talking about. So I'm showing it to you as in the context of a model, but that's what it would be known as in other variants of this type of material. So for instance, in this example, we're still predicting family income, and I want to do it by marital status. So I have this variable called married group. It gets a sub I subscript indicating that each person has a different value of these. So the intercept in my model here, beta 0, intercept always, always, always is the same thing. It's the expected outcome when your predictors are 0. In this context, that means this is the expected family income for somebody who belongs to married group equals 0. So if I set that to be unmarried persons for 0 and married persons for yes, then the intercept is specific for unmarried persons. The beta, hang on, it's typo here. Okay, find it for me. Yeah, I have 2 beta 0s. Yeah, this one should be beta 1. Yeah, see? I could pretend that I did that on purpose as a pedagogical tool, but that would be a lie. I just screwed up. Beta 1, that's our slope for the effective married group. It works out to be the mean difference in family income between people who are unmarried as the reference and people who are married, the 0 and the 1. E, the residual, is the difference in the income that is predicted by your married group and your actual income. So it's the remaining differences in income amongst people who are of the same marital level, either unmarried as the 0 or 1 as married. So here's what this looks like. This next slide always moves this over for reasons that I don't understand. So I will fix it yet again. This one. And that one. There we go. Okay. So here's my model. Y sub I, family income, equals my intercept beta 0 plus my slope for married group beta 1 plus E. So if I were to predict what income would be from this model for somebody who is unmarried, that works out to be this right here. Y hat, remember what Y hat is? Estimated or predicted, yeah, it's what the model says your Y should be. So using the example data from example 3, that's where the numbers come from, so I will show you that in just a moment. The intercept was estimated to be 25.51. The slope, beta 1, was estimated to be 26.74. Now the term in parentheses, that 0 is being plugged in to say what would predicted income be if this married group variable were a 0, meaning for unmarried persons. So this second term here, the 26 times 0, that drops. And you're left with just the intercept as how their outcome gets predicted. So 25.5 is the expected income for somebody who is unmarried because that's the only circumstance in which the rest of this drops. So E then, residual, deviation, offness, it's the income you actually had, Y sub I, minus the one that was predicted for you by the model. So this person, any person who has a status of unmarried would have the same formula here for what their Y hat is, Y sub I minus 25, and then the E would be whatever the difference is remaining relative to the 25 that was predicted for that person. So Y sub I for the other category then. Same formula, one thing that's different. Now if we want prediction for a married person, we plug in a 1 instead of a 0. And so now we need both fixed effects. We need beta 0, the intercept, to say, okay, what's income going to be for an unmarried person? Now, what do I have to add to that to get to what it is for a married person? And I have to add 26. So beta 1, the slope, is the difference of unmarried versus married. And when you put them together, you end up with a predicted income of 52 and some change. So it seems a little weird to think about a linear slope between a variable that's a 0 or a 1, but it's perfectly legit to do. Here's a picture of what this model predicts. So I have a bunch of people here on the unmarried side that are zeros that vary in income. I've got people over here on the married side that vary in income. And beta 1, the slope, is this line right here. Now note that there's nobody in the middle here. There's no such thing as married equals 0.2, 0.4, 0.6, 0.8. It's a 1 unit shift to go from unmarried to married. So the slope is just the difference between unmarried to married. Okay, how are we doing? All right. One other thing about this, when you have predictors that are grouping variables, that are categorical, although you can ask for an effect size as a standardized slope, like a Pearson correlation, it's often less intuitive than another kind of effect size. So in addition to R, I'd like you to meet D, Cohen's D, in fact, which is a standardized mean difference between two groups. So if I have group 0 and group 1, Cohen's D is calculated as the mean for group 0 minus the mean for group 1, divided by their standard deviation pooled together, where that term is right here. The good news is that you can actually get Cohen's D straight out of your output. You can convert your t-test statistic into a D using this formula right here. So if the only term in your model is that grouping predictor, the residual variance that you get back, if you take the square root of that, that is the standard deviation that's pooled. So you can get a Cohen's D directly out of your output with just a little bit of math. I usually ask SAS to do the math for me. This is one of the options that I don't know how to get it to do unless I physically force it to. It's not an option that's built into the packages. Okay. So there's 3 things that we would want to know about a binary predictor. What is the mean for the 0 group? What is the mean for the 1 group? And are those 2 means significantly different? The model will only give me 2 of those 3 pieces of information. The third is implied by the model as a linear combination. So that's one of the tricks that I wish I had learned a whole lot earlier than I did, which is why I want to teach it to you right now. How to get linear combinations of fixed effects, to get model implied terms. Because the model tells us what the mean should be for group 0 directly as beta 0. It tells us how different the mean for group 1 is, where the difference is this beta 1. And this idea right here, predicted income for married, where we add beta 0 and beta 1 together to get this new number, you can ask the program to do that for you. The advantage of having it do it for you is that it also computes a standard error for that new prediction, as well as any significance tests that are applicable. So I want to show you how to do that. So where did the numbers come from? They came from SAS. And Stata too. They gave this in this case. Ding dong.
What number are you on?
I am in example 3 here. So in your homework, the only thing that you have to do in terms of data transformation is center the quantitative predictors in the problems, such as, here's an example of how I centered education. Centering means make a new column, give it a name. So for instance, education 12 equals the old column, and then minus the centering constant. So in your instructions for your homework, if I ask you to center pleases heard at a certain number or fits thrown at a certain number, this is how you do that. You make a new column out of the old column minus a constant. The grouping variable that you're going to use in your homework is age group. You don't have to do anything for that. What? I am on page 1 of example 3. Yeah.
No, centering because it says centering in green.
The stuff in green is my notes. These are just comments.
But it helps locate what we did.
Yes. So yes, you can always, Control F for find, and you can type center, and it should hopefully pull up. What was your question, Jen? That's it?
I was just clarifying that I would find it by
Yep.
looking for the word in green,
Yes.
and then I would go under, so that's how you orient yourself.
Yeah, the lines in green is me telling you what the next line is going to do. And as you get in the habit of writing code, I would highly encourage you to leave your own lines in green that describe what the next line does and why you're doing it, right? Because it's easy to be like, oh, it's subtracting 12. And then, 6 months from now, you'd be like, why did I do that? So the motivation and the procedure. Notes to yourself, very important. So that's the only variable transformation you have to do in homework 3 is to center the quantitative predictors. You're going to use age group as is in homework 3, which is already not for this. Not anymore. It was different when you were testing a proportion, because Stata tests the proportion of 1 values, whereas SAS tests the proportion of zeros. That's no longer relevant.
But I'm not finding center in Stata.
Let me find where that is. So the Stata one, centering is right here. So this is on the second page of example 3.
Sorry, I missed it.
Yeah, no worries. Yeah, there's a lot of words in here. It's a bit of a puzzle. The only difference is that you need the phrase gen in front of it. That means generate. So that's a Stata specific, hey, I'm going to make a variable here. And the variable that you made is the next thing. So, question?
So we're supposed to center at 7, right, for
Mhm.
fits. So 0 equals 7.
Mm-hmm.
So would that be label? Fit count 7 equals fit count.
You wouldn't need, so a label is something different. So if you were just going to do this part, it would be like fit 7 or something would be your new variable if you follow my naming convention.
Right.
Equals
Yeah.
the old variable, which is called fit count,
Right.
and then minus the constant that you're centering at.
Then minus 7.
Minus 7, right?
Okay.
Or please is minus 5. It'd be the same.
Got it.
And then that version of the predictor is what goes in your model, not the original. If you put the original in, your intercept will be incorrect. So we looked at, there's 3 types of models that I'm asking you to practice in homework 3. One of them is an empty model, right here, no predictors. So it has an intercept, and it has a residual variance, that is all the variance as the 2 parameters that come out of that. The mean square error term right here, that's your residual variance. And in the next unit, I will explain what the rest of these numbers mean, but we don't need to know what they are right yet. Just that one. The Stata output looks very, very similar. The only difference in Stata is that the word intercept is replaced with a term that is underscore CONS for constant. I will pull that up actually while I'm thinking about it. So I have the full output for example 3 in available for download. Let me pull up the Stata. This is the Stata output that goes with it. So for instance, here is my empty model. Mean square residual, it's called in Stata. I like that word better actually, but SAS calls it error. There's my 1980, same relative place in the table. And then where it says intercept in SAS, it says underscore CONS. That stands for constant.
Okay, so that's the intercept.
That's the intercept, yes. That comes from a more algebra way of talking about the model, like you have the constant in the model and then you have the slope. But slopes are constants also in terms of like constant versus variable, so I think it's actually a bad name and I don't use it. It's the intercept, but that's what Stata calls it. So this coefficient header, that's your estimate. The next column over is your standard error. then you get your t-value, then you get the probability associated with that t-value, and then confidence intervals, which I don't think I asked for in this assignment, but they're there. Okay. So empty model that has a quantitative predictor, so it would look like this. So pleases, for instance, predicting fits or vice versa, where you have the centered version going in. Then there's three things you'd want to know. What's the residual variance now, which is still your mean square error, and then your two fixed effects, the intercept and the slope. So it's the slope of the quantitative predictor. In Stata, they're in the opposite order. So it lists, for instance, the slope of education first, and then the intercept last. Otherwise, everything is exactly the same. And then here's the last one that we haven't talked about yet. So this is page 6 out of 7 in example 3. So my model is family income is the outcome. Beta 0 is my intercept, and beta 1 is my slope for Mary group. So I won't know how to interpret these model results until I know who's the 0 and who's the 1. So in the version of the variable, the column that's going in that holds that's your predictor, 0 means you're unmarried and 1 means you're married. Then I know what to do. So beta 0, that's my fixed intercept, right? Intercept always defined the same way. Expected outcome when what? What's an intercept? Yeah, I'll take gestures. Yeah. It's this part, right? Expected outcome when what is true?
Like where you
Yeah, where the x's are 0. That's what the intercept means. Yeah, I won't be able to accept gestures anymore. This is going to be very sad. Unless you turn on your camera so that you can, put your slopes at me. But yes, so beta 0 is always the expected outcome when your predictors are 0. In this context, beta 0 tells me what family income is predicted to be when Mary group equals 0, which is for people who are unmarried. Beta 1 captures the difference of the 1 group relative to the 0 group. And I'm saying that deliberately, the 1 group relative to 0, because the direction tells me who's higher. If beta 1 is a positive number, a positive slope, that means the 1 group is higher than the 0 group on the outcome. The 1 group has a higher mean than the 0 group. If beta 1 were negative, it would be the opposite. The 1 group has a lower mean than the 0 group. So beta 1 carries the difference of how 1 compares to 0 for the binary predictor.
And just to recap, B beta 0 is the intercept,
Mhm.
correct? And beta 1 captures the difference.
Beta 1 is the slope that captures the mean difference between groups. How 1 differs from 0 specifically. So Mary group is the name of my predictor. That goes here in SAS, and it goes here in Stata. So up to this point, you have seen this much in SAS and this much in Stata, and now you have some new friends to make. This part right here. Estimate or lincom. Estimate is the SAS command. Lincom stands for linear combination in Stata. These commands are used to make linear combinations of model parameters and variables to give you additional predictions that the model doesn't give directly, but it still predicts indirectly. So I have two additional things I'm asking for here. The first is unnecessary, the second is necessary. I include both for pedagogical reasons so that you can see the pattern. First in SAS is a label. You can type whatever you want in this pinky purple. It's a note to yourself to say, what am I asking for exactly? Stata doesn't allow you to put a label, but I did so by including comments. So if you do // then you can make a comment inside a command. The next part, this part. What this is doing is telling SAS how to plug in values into the model to get predicted outcomes. So how do I get what income is predicted to be for somebody who is unmarried? Well, I need one beta 0. So this one intercept means I'd like a beta 0, please. I don't have to know what beta 0 is. It's referring to whatever the number is going to be. The analog in Stata is right here, where the fact that it's being multiplied by 1 is explicit in Stata and implicit in SAS. And Stata uses this const instead of intercept. From there, I'm saying, okay, now I need to address this part. I would like 1 beta 1, the slope of Mary group, and I want it to be multiplied by 0 because that's what the value would be for somebody who is unmarried. So what it's doing in terms of the math is more obvious in the Stata code because it makes the addition and the multiplication explicit. But it's allowing you to map the model equation directly onto your prediction and ask for any linear combination. So whenever you see a word in these statements, like Mary group, what it's actually referring to is the beta that goes with it, the number that the slope is going to become, or the number that the intercept is going to become. The first term in here is unnecessary. I'm writing it out for completeness to show how the model would predict income for any level of Mary group, but because Mary group is 0, the only thing that's actually being used here is the intercept. The second one is the one that we have to write if we want this additional piece of information. It tells us what the model says the mean would be for the one group.
So you use the second line for homework or something?
Yes, we do use the second line for homework. Very clever. Yes, not a coincidence. Not a coincidence at all. So yes, the second line, what it's saying is, hey, can you give me the result of the intercept plus the slope for Mary group times 1? And it does that math for you, and it gives you the standard error for that new number. So it's a linear combination of model fixed effects that we're asking for. Now we have all three things we could possibly want to know. We know what the mean is for each group. We knew what it was for unmarried because that's what the intercept means. Beta 1 tells us if the means are different, how different they are from each other, and how beta 0 and beta 1 combine to get the mean for the one group is this extra thing that you just learned how to ask for right here. How are we doing? Yeah.
What, do we also center it too then?
If the categorical predictor were not already centered such that 0 was one of the possibilities, then yes. But in this instance, the variable is already coded so that 0 is one of the groups and 1 is the other. So you can leave it alone. Just leave it just like that. If I had given you a variable where the categories were 1 and 2, then you'd have to subtract 1 to make somebody the 0 and somebody the 1 instead. So here's what we end up with. Mean square error, that's my residual variance. That's variance left over in income after controlling for marital status. So it's all the reasons why people's income differs from each other that have nothing to do with whether they're married. This table right here is the one that corresponds directly to the model fixed effects. So I've got my intercept, which is the 25. That was on the slides earlier here. What's this thing? 6 and some change. Yeah, standard error of what? Of the intercept, yes. Yes, it is the obvious answer. What I'm trying to point out is that there's now 2 different kinds of standard errors here, right? There's the intercept standard error, and there's the slope standard error.
So the first one is the intercept error, and the second one is the slope error, is that what you said?
Yep. So in the first line here, all of these numbers pertain to the intercept. The intercept has an estimate. The intercept has a standard error. That intercept estimate divided by that intercept standard error is this t-value right here for that intercept. And the probability of observing a t of 4, if the null hypothesis of 0 were true, then that would be less than 0.01% of the time. Likewise, the slope has an estimate. 26 is how much more money married people make than unmarried people. $26,000. So this is family income, by the way, which stands to reason. We'll look at personal income in the examples to follow after break. So do married people make significantly more money? Do I know that from what I'm staring at right now? So this p-value right here, that tells me the significant part. What should it be to be declared significant? Less than 0.05. Everyone has accepted that as the universal cutoff. That's our alpha level. So because this p-value is less than 0.05, we would declare it significant. Unexpected. Unlikely to have happened if there were no real mean difference in the population. Now the higher versus lower part, that shows up in one of 2 places. 26 is a positive number. So the 1 group makes $26,000 more than the 0 group. The 0 group makes $25,000. The 1 group makes $26,000 more, significantly more. And if I want to know what the 1 group makes, I have to say 25 and some change plus 26 and some change. And that's the thing we just learned how to ask for via estimate or lincom, which shows up in this additional table right here. What the model says the predicted outcome should be for somebody who is married. 25 and some change plus 26 and some change gives us the 52. So 52 is a linear combination of parameters. The model tells us what the predicted outcome would be for anybody. We just have to know how to ask for it. Okay. How are we doing? What if I switched my coding? What if I flipped who the 0 was and who the 1 was? How would this information in front of me rearrange itself? That's one thing. The 26 would become negative 26, because then I would be saying that the one group of unmarried people is lower than the 0 group of married people. How about my intercept? Would it stay 25 if I change who my 0 group is? Intercept is the expected outcome when your predictors are 0. If I change who 0 is, should my intercept change with it? My new intercept, if I switched my 2 groups, would be 52. It would be the expected outcome for the current 1 group could be 0 group. And then the linear combination that we would need to get would be the 25, the non-reference group predicted outcome. And last but not least, here is getting a Cohen's d from this result. The formula here is d is 2 times the t value for the slope, so that's right here, divided by the square root of denominator degrees of freedom. Denominator degrees of freedom is up here. That's your sample size minus the number of slopes in your model. That works out to be a d of 0.6. So the difference in income between unmarried and married people is about 6/10 of a standard deviation.
Do you have to do math for that, or does the computer do it?
I did not ask for a D for this one. In life, you would have to do it or ask SAS or Stata to save these tables and then add a new column where you define what D should be. That's what I do in practice usually, is have it save the results. So there. And as always, words. Now you know how to do a 2-sample t-test. That's what you would call this. I call it a general linear model with a binary predictor and a quantitative outcome.
Did you say 2 sample? Sorry.
2-sample meaning 2 groups. Yep. Or independent groups, that's another synonym for it. Yep. All right, do you feel like you could do this?
I'm still confused.
You're confused? Well, please, let me help you.
So that's categorical, right, because it's married and unmarried.
Mhm.
But what if you had numbers, like age, for instance? And you still just center it, and it's fine.
Okay, if you had a binary variable that represented ages, like age 3 and age 4, hypothetically?
Perhaps, yeah.
Yes. Just pulling that from nowhere.
I don't know where that came from, but yeah.
Yeah.
No idea.
The phrasing would be the same. Your age group variable would go here. Your age group variable would go here and here. And if age 3 is the 0, then if you're trying to make a prediction for an age 3, then that would be given by this line where you filled in the 0. And if you're trying to make a prediction for age 4, who is the 1 group, then that would be that line. Better?
I did something wrong.
You did something wrong?
Wrong.
Fair enough. Yes. If you want to send me, if you're asking me to help you troubleshoot, show me the code you ran and which question you're working on, and I can tell you whether or not the code is the problem. All right. Other questions? Oh, sorry. Don't play with my microphone. Well, unless I want to wake everybody up. Then I can do that. All right. Any questions from the Zoomers? I haven't heard from you guys in a while. Empty chat window. It's ominous. No. Well, it means one of 2 things. Either the Zoomers have no questions because everything is crystal clear, or they're multitasking. Let's see if anyone writes back. I'm not multitasking, says Dre. If we have questions during your office hours, can we do it over Zoom? Yes. Yes, I plan to keep the Zoom window open all day long until 4:30. So, yep. Do you have a screenshot of the way SAS's output will look like? For this type of analysis, yes. In homework, or excuse me, in example 3, I saved all of the output that goes with the example. So this is straight from SAS. If you ran example 3 from start to finish, you'd get all this stuff. So here is what we just talked about would look like. Lots of pictures. Talk about what those mean at some point later. There we go. Nope, not yet. There we go. So the SAS output that goes with the syntax and the handout that I just showed you, this is in their HTML output, which is harder for me to paste and work with, but much prettier to look at. We've got, for instance, your residual variance right here. We've got some extra pieces of output that you don't need. This table right here is the estimate statements, the linear combinations, and this table down here are the model parameters. So yes, in my handouts, I get rid of the extra stuff that you don't need to try and limit the amount of output that we have to focus on. The other tables will become relevant as the models get more complicated. Okay, does that help? And do you want to see the Stata version? Yes, thank you. Good. Okay. It's right here. Stata doesn't make lots of extra pictures unless you ask it to. So Stata has it in a slightly different order. It prints the table of fixed effects that are model parameters first, and then it gives you in separate little tables the results of each of these lincom statements that give you linear combinations. So here's the first one, and then here's the second one. So SAS concatenates those into one table, Stata spits them out separate.
So it was just a test document from the example 3 folder download? Is that where you go?
The example 3 download, this is the log file. So it's the name of this file is examples3 stata output.log. Yep, it's just a plain text file that you can open in any package. All right, good. Well then I wanted to make sure we get through that, and then we have a couple other things to go through then, if no one has any more questions about binary variables. Then you'll get a chance to practice that on your homework. We have quiz to go over and homework 2 to go over. So let's look at formative assessment number 3 real quick. I looked at these this morning. Your grades, by the way, are updated inside the homework portal with all the possible points that are out there as of right now. So this was due last night, and thank you everybody for doing it on time so that we can go over it together. So first question was, in null hypothesis significance testing, what is the role of the null hypothesis? Some confusion on this one. The null hypothesis is your benchmark. It doesn't have to be 0. It's the reference point. When you are testing measures of association, so for instance, Pearson's correlation, it is almost always the case that the null hypothesis is no correlation. But it doesn't have to be. If you had good reason to expect that the population correlation is 0.5, and you want to know how your sample stacks up relative to an expected correlation of 0.5, then 0.5 is your new null hypothesis. That is called a non-nil null. I know, right? I can't even make that up if I tried. A non-nil null. That's what that would be. When we did examples of univariate hypothesis tests, like testing whether the number of fits thrown was different than 4, the number of pleases heard was different than 10, that kind of thing. The different than, that's your null hypothesis in that context. It's what's expected. And you're trying to see how your sample mean relates relative to that expected. So null just means that's sort of what you're testing against as your expectation. It often does 0 in measures of association, but it doesn't have to be. What does it mean when you say you reject the null? Give me all the synonyms you know for this term. Unexpected.
Do not.
So reject the null is unexpected, is significant or non-significant? Significant, yes. I almost said insignificant. That's how tired I am. Don't say insignificant. That's a value judgment, not a statistical term. Yeah, so when we say we're rejecting the null, we're saying we have evidence to suggest that what we found is really unexpected. If the null were true, what we found would be what we found would happen less than 5% of the time, if that's our alpha level. Then the opposite. What does it mean if we say retain or do not reject? Non-significant or expected. Yeah. It's well within our range of what we would expect of fluctuations. We don't have enough evidence to say that we reject the null. We don't accept the null, but we just say we do not reject. That's a great question. I'd have to look it up. I don't know the answer off the top of my head. Null, yeah. It's null hypothesis significance testing is a phrase that like people made up a long, long time ago to describe this process. But yeah, null meaning, it's not 0 exactly. It's expected.
Well,
Yeah.
it says, our friend Google
Yes.
says it's from the Anglo-French null, NUL, which means not in.
Not in. Okay. So Google University says null means not in. I like it. Non-nil null. Yeah. All right. So in terms of decisions, if there's 2 ways that we can screw up our decision-making process: type 1 error, type 2 error. So what is a type 1 error first?
Reject the null, and indicating that there is a difference when there is actually no difference.
Yes, we say we found something, we reject the null, but we're wrong. That's alpha, Greek letter. Otherwise known more simply as a false positive. Type 2 error then, it's related to power. 1 minus type 2 error is power. But what is a type 2 error? What kind of decision problem have you made? Created, I should say. You retained the null, but you weren't supposed to. You missed something. You said, I don't got anything. It's well within expected, but really it was unexpected. That's a type 2 error. What is the conventional level in the social sciences of type 2 errors? Do you remember this? We talked about it briefly one day. So we set alpha at 0.05, right? Everybody's just agreed that that's what it should be pretty much.
Mm-hmm.
So type 2 error is beta, not to be confused with fixed effects beta, of course. They had to reuse the letters. But what's the conventional level of type 2 error that we accept? See, this very close. 0.8 is for power. So it's 0.2 for type 2 error. 1 minus power is type 2 error. 1 minus type 2 error is power. So yes, a power level of 80% is what we desire. By convention, that means we are willing to accept a 20% false negative rate, a miss rate. So then that is a nice segue. What is power? Are those gestures? I'm going to need a translator on that gesture. Balance. How so? Yes, you can give a circular definition if you'd like. Yes, power is, power is 1 minus the rate of type 2 errors, beta. Yeah. Well, if type 2 error is not finding something we should have found, then the opposite of that is finding something we should have found. Finding something when you shouldn't have is type 1 error. That's the other, like, family. So we're over in should find something. Power is the probability that you find it if it's there. Type 2 error is the probability that you don't find it if it's there. And if you want to have more power, you need more what? People. People are power. And you also need what? Some confusion on this.
Alphas?
Alpha is, I thought of that after when I was reading your answers. Yes, you would want to have a large alpha to have a better chance of finding something. But assuming that alpha is fixed, it is effect size. It's the signal to the noise. If you have a correlation of 0.7, that's going to be easier to find, to declare significant, than a correlation of 0.3. It's a stronger effect. If you have a correlation of 0.3, that will be easier to find if you have a lot of people than if you have only a few people. So in designing research studies with quantitative methods, one of the things that you will probably be asked to do is provide some sort of estimate of your power. And there's two ways to go about that. One is to say, okay, this is the effect size that I expect to find. How many people do I need to reliably find that effect? The other way, which is the more honest way, is, okay, I can afford 50 people. What will that buy me? That is what's known as a sensitivity analysis, by the way. It's a term. And if I want to know it from that more honest perspective, because usually budgets and logistics are fixed, that's where we get out our happy little power tables. We looked at those a little while ago. So for instance, here's D's. If I can afford 50 people, well then this is a D. Is it per group or both groups? It'd be 25 per group if I were looking at mean differences. So that would be somewhere around here. That means that at 80% power, I could detect a D of 0.8 or bigger. What if I could find more money? And I could afford, say, 66 people instead of 50. Now I'm over here. Now I can get a D of 0.7 with 80% power. So these are standardized mean differences. The other effect size metric you know is R, which is in correlation units. So if I had 50 people and I want 80% power, that's somewhere around here. An R of just under 0.4. So if you go out here to the top of this table, ginormous R's. If you have a ginormous association in your population, it takes like 6 people to find it. Does that happen? No. Not in the social sciences. Yeah, I wish, yeah. Yeah, this is I have helped people write grant proposals where they do randomized control trials. Have you heard this phrase before? Where you randomly assign groups to things. And let's say that you have schools as your groups. And you have 5 schools in the control condition and 5 schools in the treatment condition. It does not matter how many students you have because your power is at the level of the school. So I have written grant proposals before where people had that kind of sample and I had to say things like, we have 80% power given the present design to detect an R of 0.9 or greater. Which is sort of hilarious because good luck, right? But that's the reality. So knowing how sample size and effect size play together to influence power is one of the things that will be helpful in deciding how many people is enough and not overkill. All right, so questions on that so far? last question then, how would you know which type of bivariate association and corresponding effect size you should use? The big picture answer? What kind of variables you have? If you have a pair of quantitative variables, what do I do with that? Pearson's correlation, or I could put one as a predictor of the other in a model. What if I had a pair of categorical variables? The other Pearson, yeah. Chi-square, yes. What happens if you run a Pearson's chi-square on quantitative variables? Several of you did this by accident, so I know you know the answer. If you put in a pair of quantitative variables and ask for a cross tabulation using, say, tab2 in Stata or proc-freq in SAS, what do you get back? Big, ugly chart, correct. Now, why is it so damn big and thus ugly? Because it lists every possible value of your quantitative variable and combinations across variables. It doesn't understand that they're numbers. It's tallying up the number of possibles. So it isn't a measure of association in the way that we're thinking of it as two quantitative variables. It's not a Pearson's chi-square. The only time Pearson's chi-square and Pearson's correlation are equivalent, can be made equivalent, is for two binary variables. Then one is a linear combination of the other. Pearson R is, if memory serves, square root of chi-square over sample size. Pulling that out of my memory, which is always tricky. I wanted to point that one out because that one had a lot of questions about it too. Yeah, very close. Square root of chi-square over sample size. That's how you convert a Pearson's chi-square between two binary variables to an R. That thing is called a phi correlation, by the way, but it is the same thing as Pearson's R. It's just a different name. Do we know any others? What about ordinal variables? You know one for that, right? Another kind of correlation, different old white guy. Experiment, there we go. Yes. Well, they named stuff after themselves or someone else did it for them. I'm not sure which, but that happens a lot in statistics. And everything, yeah. All right. So questions on this? All right, then if not, then I want to go over the answers to homework 2 with the time that we have left, about 10 minutes or so. So you should all be able to see what the correct answers would be. I have one of your homeworks in front of you, so this is one person's set of numbers. I will note that the right answers down here are tied to this individual data set. So what the answer that is correct is for you may not be the same answer that is correct for someone sitting next to you because it's tied to your data. So for this person, you all have the same tendencies in your data, but it's not a one-to-one correspondence. So for instance, what is true about the proportion of students who are 3 years old? Well, we know from up here that that proportion in this person's data was 0.82. And the questions are asking, okay, how does 0.82 compare to 0.6? Well, 0.8 is bigger than 0.6. Okay, so I can narrow this down to these two choices. How do I know if it's significant? P-value. If for a proportion test, where does my p-value come from? What letter? Yeah, this one's Z. Yep. And it's because we don't have to estimate a variance to do it, because in binary data, the variance is determined by the mean. That's why we get to use Z. So for that test, the Z value is right here. The p-value that goes with it is less than 0.05. So yes, the result is significant, and because 0.8 is greater than 0.6, it's significantly greater. Same logic for the next one. Proportion of students who have Miss Molly, 0.49 and some change, relative to 0.5, that number is smaller. How do I know if it's significant? Well, I have a z-test for that. There's my z, there's my p. Note the z is negative. That tells you that it's smaller than expected as well. And because the p is much greater than 0.05, we call that non-significant. Association between age group and classroom teacher. There's two ways you can think about this. The way that I'm encouraging you to think about it with these options is comparing the expected frequencies to the actual ones. And so these words are focusing you on the combination of the cell with Miss Molly and 4-year-olds. And so you were to look at what was the real frequency relative to the expected and decide whether there were more 4-year-olds than expected or fewer. And then how do I know if it's significant or non-significant for this pairwise association?
We're looking at the, Pearson.
Yep, this is my chi-square, yep. So here's the chi-square. I can convert that chi-square into an R, which is right here. So Pearson's chi-square is a test statistic. It tells me whether or not the result of observed versus expected is significantly different. Here's the p-value that goes with my Pearson's chi-square. Pearson's chi-square is not signed. It's in a squared metric. It only has positive values, so you can't look at the sign. That's why you'd have to look at the pattern of expected frequencies. The correlation that goes with that is right here. It's a negative correlation. So that negative correlation means as x goes up, y goes down, right? So if I want to say x is age, so as x goes up, as you are 4 years old, y goes down. That would be Beth versus Molly. That means 4-year-olds are more likely to be with Beth if it's a negative association. So there's fewer 4-year-olds than expected in this person's data set. It's hard to think about correlations between binary variables sometimes, but it's the same logic works. As x goes up, y goes up. That's positive. As x goes up, y goes down. That's negative. Goes up means is more likely to be the 1 instead of the 0. Or is more likely to be 4 than 3. Is more likely to be with Miss Molly than with Miss Beth. And yes, Beth and Molly are real people. They are the teachers at my son's school. My son is in Miss Beth's class. Some of his best friends are in Miss Molly's class. And they're both angels for putting up with all of these 3- and 4-year-olds. 20 of them in a room. Yeah. That's a noisy crowd, correct. Question 55. What is true about a Pearson R as a linear relationship between age group and classroom teacher? So a lot of questions on this question and the one like it below. Whether or not it's valid. First off, to me, valid means, does this even make sense to think about as a number? And because you can get a Pearson's R out of the chi-square for these two variables, this formula right here has to be valid. In the instance of both binary variables, it is okay to fit a Pearson's correlation between them. However, it is valid, but it's not the best way to measure an association because it is subject to range restriction. Let me find that slide. This one. If you have two binary variables whose means deviate from 0.5, the maximum association that they can show is not 1. It will be some factor less than 1. That's a range restriction problem. And all of these words on the next slide, this is slide 36, are advanced statistics classes ways of dealing with this problem. These are not things you can calculate. These are things that are estimated. And if you come back and take more classes from me, You'll get to hear about them. Like this fall, I'm going to talk about tetrachoric correlations and polychoric correlations, and it's going to be awesome. So that's where I come up with my answer. Yes, it's valid, but potentially subject to range restriction. And in this context, it is, because the split of 3-year-olds and 4-year-olds was roughly 80-20, and the split of classroom teacher was 50-50. So the maximum association those variables could show is going to be less than 1. Okay. Quantitative ones. So the first two are similar to the proportions. You are being asked to compare a mean to a hypothesized mean. So whether or not it's significant, in this case, comes from a t-test, not a z-test, because we have to estimate variance in order to get the standard error for this test. But the t being significant or not tells you whether that first part, and then greater than or less than 4, is relative to how your mean compares to the target mean. So let me find, for instance, number of fits, almost 7 fits on average. That's definitely more than 4. And here's the p-value that goes with that from this one. Same thing about pleases heard. It's definitely smaller than 10. Confidence interval and a sample mean. Had some recent questions about this. So if your interval does not contain the hypothesized one, that's a reject. That's a significant. If it does contain it, that is a do not reject, a non-significant. So the only ones that are right then are the middle two. They convey those two options. Question 59. Neither Z nor T are effect sizes. They're test statistics. They are a combination of effect size and sample size. So the correct answer is 2. 3 and 4 were incorrect because they're backwards. Z is used when a variance is known. T is used when a variance is unknown. And then we have Pearson's R. So if R, for instance, is significantly negative, and we're talking about the association between pleases and fits, then as fits goes up, pleases go down. So the correct answer, if it's significantly negative, is greater fits is associated with fewer pleases. In the next instance, fits thrown in age group is significantly negative. So more fits, as fits goes up, age goes down. That means more fits, more likely to be a 3-year-old. Pleases heard in age group, if that's positive, then as pleases go up, age goes up. So more likely to be a 4-year-old if you have more pleases. And then the last one here. I asked you several questions about favorite TV show that were stupid questions. They were dumb, but I did that to make a point. So for instance, the mean of favorite TV show. The scale of this variable, I can remind myself, 1 is Paw Patrol, 2 is PJ Masks, and 3 is Peppa Pig. What the hell does a mean of 2 mean? These aren't numbers, right? SAS is quite happy to give you a mean, a standard error of the mean, or anything else that you want, but it makes no sense. So I was hoping that as I asked you these things, there'd be a little thing in your head that went, what does a mean of 2 mean?
I was like SAS. I was having to confuse.
Oh, it's your green, cool.
Yeah. Fair enough, fair enough. And then I asked for correlations between favorite TV show and other stuff. And the answer is that none of that makes any kind of sense. Because favorite TV show is not a number. And there's 3 categories, which means that there are 3 potential differences you could have between fits thrown. Do people who throw more fits like Peppa Pig better than PJ Masks, Peppa Pig better than Paw Patrol, or PJ Masks better than Paw Patrol? Each of those 3 things could differ in terms of fits thrown. So we can't draw a single line through the 1, 2, 3 and have it mean anything. So it is not valid. The end.
So if there was 2 TV shows, would that be different?
If there were two, then it would be okay because there's only one difference. And that would mean, like, if there was no Peppa Pig, right? And then that would be like people who prefer PJ Masks over Paw Patrol throw more fits or throw fewer fits. But we can't have the 3 in there, and you can't have the 4.
But there would still be range restrictions.
Potentially range restrictions if they were binary, yes. So the same problems, it's just that the fact that it's a nominal variable, that just shuts the whole thing down. How to put a nominal variable into a model is what we're going to do after break. That's the next unit. All right. Does anyone have questions about these? I realize we're running over a minute or 2. All right. Well, if you do, please email me or Zoom with me, and I'm happy to talk to you. Have a good break, everybody. Do some self-care. Stay well. And I will see you in some form
Yeah.
in a week and a half, give or take.